The interior point method is a numerical optimization algorithm for robust collision resolution. Its robustness relies on repeated invocation of CCD after each nonlinear iteration. This makes the interior point-based simulation highly expensive. For instance, this dragon model consists of 1 million tetrahedral elements. 1 Newton iteration takes nearly 400 seconds to simulate just one time step. In this paper, we propose a new GPU algorithm to efficiently simulate high-resolution elastic models using the interior point method. Our method starts with a novel complementary coloring scheme, which is robust against varying collision patterns and can be pre-computed before the simulation. Each time step initializes a warm start processing first to effectively damp high-frequency impulse-like barriers. The parallelism is enabled by solving 12 by 12 subsystems at stencils in parallel using Newton CG relaxation. We design a hybrid sweep strategy, aiming to fully exploit the throughput of GPU. As a result, our method delivers speedup up to 2 orders in complex and collision-rich simulation problems. For instance, this barbarian ship consists of 487,000 elements. Our method only needs 12 seconds to simulate one time step, while CPU-based Newton's method uses 20 minutes. This is over 90 times speedup. We make the body of the ship 5 times stiffer, and put one more ship into the simulation. In this more difficult test, our method offers 129 times acceleration and produces high-quality animation. Here is another challenging simulation test. The puffer ball has 610,000 elements, while the net has over 300,000 elements. The dense interactions between the strings on the ball and the net yield interesting animation. Our method is versatile and can simulate heterogeneous materials with both rigid and soft components. To show this, we make the chain net rigid using affine body dynamics, and 6 helicopters fall onto the rigid net. There are 1.7 million elements in this experiment, and our method is 122 times faster than the original ABD algorithm. Our method can also simulate codimensional models robustly. In this test, we show the strong coupling between 2 bone dragons and a piece of tablecloth. And our method is 72 times faster than codimensional IPC. Here, we compress a Voronoi cube and compare the result with the one calculated using Newton's method. Our simulation result is nearly identical to the ground truth. We visualize the error with color map, and the maximum relative error is below 1%. Finally, we show a stress test with 5 puffer balls. There are 3.1 million elements and 2.3 DOFs in the simulation. Even 128 G memory is not sufficient for using a direct solver, while our method can finish this simulation smoothly. Our method uses 5 minutes to simulate one step, which takes several days on CPU. Thank you for your attention.